So, good afternoon, everybody. I will continue on the chapter 1 for this course on population and society. I just wanted to let you know that I posted the lecture from last Tuesday on my YouTube website, YouTube channel. So you can, in that link, you can just go here to the syllabus. It's going to be this one. And if you go to the YouTube channel, I will put all these videos related to this course on this playlist here. Introduction to Demography Fall 2021. The microphone stopped working after 1 hour and 1 minute last class. So this video here has 1 hour and 14 minutes, a little over than that. But so in the last 14 minutes, there is no audio. Okay, so that's the issue there. I always have this kind of problems in the first day of classes and the last 2 semesters as well. I will try to also record the lectures with that video on top there. So if you're watching from home afterwards, at least you know where I'm pointing and stuff like that. But I'm going to try to point for graphs and maps when I'm interpreting them with the mouse, so it's easier to watch from home. We stopped on our last lecture on this slide about the basic demographic equation. And I was pretty much mentioning that we can estimate the size of the population of the next time period based on information from the previous time period. So let's just think that we have information of the population in January 1st, 2020 for a specific state or for a specific country. Let's say a specific country, January 1st, 2020. And we know the number of births that happened in that specific country between January 1st and December 31st, 2020. So we add that those people who were born in 2022, the population at the beginning of the period. And we subtract the number of people who died in that same year from January 1st to December 31st. If we are talking about country, in this example, we have also to add the number of people who entered that country in the same period. So these are immigrants. And we have to subtract the amount of people who left that country within that same time period. So we have the estimation of the population in January 1st, 2021, in the following year. This kind of analysis can be done not only by year, can be done by month, but of course, by month is much harder to get so detailed information to complete the data in this equation. And also we can do this similar kind of analysis if we are talking about subnational areas. So if you're talking about Texas, when we are adding the number of people who enter Texas in that specific time frame, these people can be both immigrants, people coming from other countries to live in Texas, or from other states within the US to live in Texas. So we are counting both immigrants coming from other countries and migrants, people coming from other states within the US. And we have to subtract the number of people who left Texas. Maybe some people left Texas to go to other countries, those are immigrants, or some people left Texas to go to other states within the US, those are out migrants. Okay, so that's the basic demographic equation. Seems really simple, but it's actually really helpful. And it provides us information to do what's known as demographic projections based on previous trends of population size, trends and levels of population size, births, which is related to fertility, deaths, which is related to mortality, and immigration and emigration related to migration. Based on these previous trends and levels on these indicators, we can try to make some simulations of the population size to the future. That's how we are able to estimate the population for a specific country for the next 10, 50, 100 years. It's all based on this simple equation. But since we are trying to look at the future, we have to look at the historical trends and try to imagine if those trends will continue, if we can have some variations like decline in fertility, increase in mortality because of the pandemic, for example. In all these different scenarios, it gives us different projections, right? So, but our scenarios, our simulations have to be realistic. The more realistic they are, the more they relate to what we are living, better our projections will be in the future. And with this basic demographic equation, we can have an information about whether the population is increasing in size or whether it's decreasing in size. So this term, natural increase, means that in a specific time point, in this case, in this example I gave, January 1st, December 31st, 2020, if the number of people being born is greater than the number of people dying, the population will increase. That's what we call the population experience a natural increase. Natural decrease is when we have less births than deaths in a specific time point for a specific population. The natural decrease can also be referred as negative natural increase. I just think that those two terms are easier to understand. And see here in these two terms that demographers use a lot, whenever we're talking about natural increase and decrease, we are taking into account only information about fertility and mortality. Natural increase and natural decrease is not taking into account information about migration, immigration and immigration. So whenever I'm talking about natural increase, I'm comparing the overall levels of fertility and mortality. Maybe you can close that door because of the noise, please. I think they're already closed. Thank you, appreciate it. And so, for example, one country might have fewer births than deaths in a specific time period, so it would experience natural decrease, decline in population size, but maybe that country is receiving many more immigrants than losing people. So maybe in the next year, instead of the population size declining, as we would think just by looking at natural decrease, the population can actually increase because they have too many immigrants. So it's just to show that these two terms, natural increase and decrease, is just to have a general idea based on fertility and mortality, but to actually know if the population is going to increase or decrease, if you're doing some population projections, you also have to take into account migration, composed by both immigration and immigration, okay? In the terms of immigration and immigration also give us some helpful information. If we subtract the number of immigrants by the number of immigrants, we have the net international migration information. If we are talking about migration between countries, if my unit of analysis, I'm doing that demographic equation for countries, when I subtract I minus E, I have net international migration. But if I'm doing that analysis for a specific state in a specific country, and okay, I'm also talking about people moving to that state from and to other countries, but I'm also considering the number of people who move to that state from other states within the country or moving out to other states. So the I and E refer more to internal migration, and the subtraction of these two terms is called net internal migration. When the term I is smaller than the term E, we have a negative net international migration. So there are more people getting out of that specific area, that specific country, than going to that specific country. So we're going to encounter negative net international migration in sending countries, what are called sending countries. Of course, sending countries also receive people moving to their area. But overall, there are more people moving out than moving in. If you're talking in terms of internal migration, whenever the number of out migrants is greater than the number of in migrants, we have a negative net internal migration. So a specific area has a net out migration, more people getting out to other areas within the country than going in. And then the opposite, more people moving in than moving out. That's called a positive net international migration. That's the case of receiving countries. That's the case of the US, for example. The US receive more people within a time period coming from other countries than America's moving permanently to other countries. And positive net internal migration, that's the case of the state of Texas. Texas has a net in migration, which means that Texas receives more people from other states in the US than people moving out from Texas, okay? So with that basic demographic equation, we can, if we have all those terms, we can already do some analysis about what's going on in specific countries or specific states. And if we have that information for different years, you can start to look at trends and kind of try to predict how the population is going to be in the future. Usually, it's the levels of fertility and mortality don't vary as much. Of course, in the case of a pandemic that we experience now, mortality is increasing a lot compared to other years, and that affects fertility. People postpone having children. But usually fertility and mortality don't vary so much. They're more stable over time. They're in low levels and stable. Fertility around 2 children per woman on average. But migration varies a lot. Immigration and emigration, and even within countries, varies a lot, depending a lot on public policies, on different policies that are implemented by federal government or state governments, okay? So these two terms here are harder to project to the future because they oscillate a lot. Fertility and mortality are more stable, so it's easy to predict how they're going to be in the future. So population projections have the difficulty of estimating good scenarios, simulations to the future, of trying to predict how the migration terms here will be in the future. Cool? Now I start another subtopic in this lecture, and this is kind of like outside of the main textbook. That's from another textbook, which is pretty much Introduction to Social Statistics, Introduction to Statistics to Social Sciences. And here I just want to explain what are variables and observations, and also explain what is a database, what is a microdata. Just because these terms, variables, observations, we're going to hear a lot. Whenever you have a course, usually like in social science, that deals with data analysis, empirical analysis, we always refer to variables, characteristics of people, collecting observation from specific units of analysis, and organizing that information in database. So it's just good to have that clear. What are those things? So variables are characteristics that can change values from case to case. If I do a survey in this classroom here, like in total, we have, I think, like 71 students enrolled in this class. And then I just passed to you a questionnaire asking information about gender, age, race, ethnicity, number of children that you have. Probably it's going to be really low or nothing because they're all really young. Place of residence of parents, your income, and so on. So that all this information, all these characteristics that I'm trying to get from each one of you are called variables. And these variables, they vary across my cases. And these cases that I'm talking about in my example are you guys, students on SOCI 312. So the observation, the cases, refer to the entity from which data are collected. We also say these are the unit of analysis. And in this case, I give example like individuals are my unit of analysis, but it could be households. I could send a questionnaire to a specific household, and instead of asking questions about gender, age, race, ethnicity of each one of the people in that household, I could just ask, how many people live in this household? What's the overall income of the people in this household? Like adding all income together from everybody inside. How many rooms do you have in this household? How many bathrooms you have in this household? So the unit of analysis will be households. I can also collect information for states. I can even look online and get information about employment rate, about race, ethnicity, composition, proportion of African Americans, proportion of whites, proportion of Hispanic in each one of the states in the US. I can get information about total fertility rate, the average number of children that people have in each one of those states. So in this case, I'm getting a series of variables, characteristics of my state. So my database, the unit of analysis is going to be the state. I could do a similar thing for countries. I could collect information for countries. What's the population size of this list of countries? How many, we can do the same kind of variables that we just did before. What's the employment rate? How many people were born in these countries in this specific year? How many people died? So we are getting characteristics, variables for these countries, and countries are my unit of analysis in this example, okay? So this is just, this next slides here is just explaining that. Variable, characteristic, whose value varies from case to case, and we can collect it from the people and quantify it. And we usually group variables in these two different kinds, a dependent variable and an independent variable. Dependent variable is a variable whose variation depends on another variable. It's the result of all the characteristics of my unit of analysis. Independent variable is a variable whose variation causes variation in my dependent variable. For example, income. Let's think about income as a dependent variable. What are some other variables, independent variables that we could try to collect from people that would explain their income? Profession, education level, number of jobs, location. Usually people who live like in bigger cities have higher levels of income. Age, because usually older people have higher income up to around 56, and then after retirement, it tends to go down. Number of years in the labor market, sex, women on average receive 30% less money than men, controlling for all these characteristics that you just mentioned. Race, ethnicity, African Americans also receive much lower earnings on average than whites, controlling for all these characteristics that you mentioned. So, yeah. Parents' income also influence my income. Did you raise your hand? No. Mother's education is a good predictor. Mother's education usually explain a lot my own level of education and consequently my income. So whenever we are doing research, in this case, I'm trying to understand what are the factors that influence income, either increases or decreases income. I have to think about a series of independent variables that will be the causes of variations in income, right? So that's how a research starts. What my research question? My research question is trying to explain variations in my dependent variable, in this case, income. I have to look at all the previous studies that show that income varies by all these characteristics that you just mentioned. So I have to create a questionnaire that will capture information about all these variables, right? And I have to collect this information. And one way we usually use these terms, dependent variable and independent variable. And what we are trying to do is use previous knowledge that people try to explain variations in that specific dependent variable, previous knowledge from previous years, from other countries, from other areas, from other populations in general. And I try to see if those theories apply to the specific context that I'm trying to do. So, my research question: what are the factors that influence variation in income in Texas in 2021? And then looking at previous research that gives me all this background of knowledge, I come up with these possible explanations, my independent variables. So this previous knowledge, the previous theory, gives me possible explanation about what is causing variation in income. Based on this previous knowledge, I say, oh, I have a hypothesis. Based on this previous knowledge, I think that older people will have higher income. People living in big cities will have higher income. Men will have higher income. White will have higher income, controlling for everything else. What am I doing now? I'm answering the question, the research question, before I even look at my data. The answer to a question before I look at the data based on my knowledge from theory is called hypothesis, right? So hypothesis is the answer to a question, to a research question, based on previous knowledge, based on theory. Overall, if you're watching the news, if you have like people discussing a specific problem in a more informal way, people say, oh, I have a theory of why this is happening, and then they give their explanation. The correct term is not theory. I have a hypothesis about why this is happening. And my hypothesis is based on this previous knowledge, on these theories that were previously developed about that specific topic, okay? And these theories and hypotheses, they're stated exactly trying to explain variations in the dependent variables, which are the results and effects of my independent variables, which are the causes that result in my dependent variables. This term, dependent variable and independent variable, is really common in econometrics, in sociology, in social sciences as a whole, but you might see other names for the same variables: explained, explanatory, response, control, and so on. Sometimes I try to say, okay, I know that income is explained about all these other variables that we have for this population. I just want to control for those variables, but the main variable that I'm trying to understand in this specific research is education of mothers. I want to control from everything else that we talked here before. I will control because the previous theory said that they are important. So I'm controlling for them, so I can call them control variable. Although they are independent variables, sure, we're just going to call them control variables because I'm controlling, but I'm not really interested in interpreting them. I'm interested in interpreting the effect of mother's education on my income. Okay? So, but this is just to show you that we have different ways of calling dependent variables and independent variables depending on the field where you are. Observations, like I said before, collected information used to test hypotheses. We decide how variables will be measured based on what's the unit of analysis that I'm gonna have. I'm trying to measure social reality, and usually in this kind of analysis, we collect numerical data. All sorts of information here that we collect. Sex is all collected in numerical way. Usually 1 female, 2 male, for example. Race ethnicity, the same thing. 1 non-Hispanic white, 2 non-Hispanic African American, 3 Hispanic, 4, and so on. So we collect all this information. It's organized in a numerical format for analysis. And all this information, it's organized in databases. My database, it's going to have the variables as columns and the observations as rows. So this is one example of a database. We interviewed 526 workers, and we asked what's their salary per hour, years of schooling, years of experience in the labor market, how many years they have been working, whether they are women or men, and their marital status. And the marital status information here is also simplified, 0, 1. Married 1, everybody else 0. Of course, for all these variables, we can measure them in different ways, okay? So this is a database. The variables are my columns, the characteristics of these workers, and the rows are my observations, the unit of analysis. Each one of these numbers here are my individuals. And then I can do some analysis with the statistical software, because this is a really big database. It would be hard for me to generate summary tables about that. But for example, let's just look at the 5 first rows here. Or let's just first, before that, we have 526 rows in this database. These data, let's say that I send a questionnaire to all these workers and they answer it to me, and then I put it afterwards in the computer. And when I have this full database is called microdata. Microdata is this disaggregated database in the original way that I collect the information. But this is not really helpful to try to understand the variables. It would be interesting to know what's the percentage of women in this database. What's the percentage of married people in this database? Just looking at the first 5 rows, what would be the percentage of women that were interviewed? Thinking that we interviewed just these first 5 people. You would have 40% of women, right? We have 5 cases and 2 women, and 60% of men. These 5 cases, how many are married in percentage terms? 60%, and the others, 40% are in other marital status. So in this case, I'm creating tables. I'm aggregating my data. When we have, for example, election political poll that we always hear, right? Oh, this candidate has 45% of the electors said that they would vote to candidate A. And that information was collected after the microdata was collected from everybody. We ask if that person would vote for candidate A or not, and then we can estimate that percentage. Or we can simply ask, are you going to vote to candidate A, B, or C? And we can also ask marital status, we can also ask sex, we can also ask age, we can also ask income, and then we can make cross-tabulations. We can say, among men, what's the percentage that is going to vote for candidate A? How many to candidate B? So those tables, cross-tabulations, because we have 2 variables, candidate and sex, was estimated, that cross-tabulation, that aggregated level data, was estimated using a microdata, right? So based on my database, my data set, my microdata, I can create a series of different tables. If I'm doing a table for one specific variable, 40% of women, 60% of men, that's a frequency table, one variable. Out of the women, how many are married? In percentage terms. 50%. Out of the women, 50% are married, 50% are not married. Out of the men, 66% married, 33% not married, right? So if I had a database with 526 rows, I would not do this by myself. I would use a statistical software to do that. But it's just to show that variables, we collect information characteristics, in this case about people, and then afterwards we can play with the data. We can estimate frequency tables and cross tabulations. That's exactly what is done in these political polls, for example, election political polls. One example of a database, it's about the current pandemic. This is data from August 24, 2020, when the fall semester started back in 2020. And for all this data that I'm showing here, I'm showing in the bottom of this slide, the source of the information. So this one here is from Worldometers, this website that's collecting data from all these different, like in a continuous basis. And here I just got the screenshot for the top 20 countries with the highest number of deaths, right? They sorted by deaths here, US, Brazil, Mexico, India, UK, and so on. So this is one example of a microdata, a database, a data set. My variables are name of the country, total number of cases of coronavirus up to that date, new cases, total number of deaths, total recovered. And if I get the population, I can get the total number of deaths, total number of cases divided by population multiplied by 1 million. I have this indicator. Number of deaths divided by population multiplied by 1 million. I have this indicator, this death rate and this case rate. If I get the number of tests here divided by population multiplied by 1 million, I have the test rate. So this is a database. With this database, I can make a series of analyses about the pandemic in the US and in all these other countries. Oh yeah, variables are my columns. My rows are my unit of analysis. In this example here, the unit of analysis in this database are countries. Each row is a country. And then on Tuesday, last Tuesday, I went to the same website and I collect the same information. Here, I mean, I'm showing 21 countries. If the top 21 countries will be like the same 20 countries, but now sorted by number of deaths, now in 2021. UK went down, Peru went up, US, Brazil, India, and Mexico is still up there, right? So now I can do some analysis over time by country in terms of cases, deaths, recovered, and so on for each one of these variables that I have collected. And if I had done that, I could have collected this data on a daily basis. Of course, Worldometers, they have that in their server, but they show in the website just information for that specific day. But I can do the analysis and see variations over time from 2020 to now, 2021, for these countries. And we can go further. In this case here, I'm getting this data from this other website, Our World in Data. And I selected the 5 countries with more deaths according to Worldometers. The 5 countries with more deaths 2 days ago were USA, Brazil, India, Mexico, Peru. And I just went to this data, to this website, and I selected those 5 countries. It's a little hard to see this graph here because the way when you selected, the colors of India and the US are really similar to each other. And you can select different things. In this case here, I'm just showing from the beginning of the data that they have available there until August 31st, the daily new confirmed cases of COVID-19. So the US is this one here, had increased a little bit in the fall 2020, and then increased around Thanksgiving, Christmas, and beginning of this year, decline, probably related to vaccinations, and increase a little bit, like I think this would be around April, decline, and now increasing again related to the Delta variant, right? And India is this other one here, increase here around September, October, increased a lot around June, July, and now decline, right? So here we have the big numbers, how many cases we have been observing in these countries. If you just go to this database, you can select different countries and you can select also different indicators, different variables, different columns from data set to show in the graph. See, the graph is already not aggregated level information. Just think about that database that we saw in the previous slide. This database is for one specific day. Here, we have information for each one of these days here that we have in this graph. And it's summarizing everything in this figure. So it's an aggregated level data analysis. One limitation of this graph is that the population of India is much higher, it's much bigger than the population of these other countries. So we should take into account the population size. An easy way that we saw in the previous graph is just to take the rate of cases, get the number of cases divided by the population. And that's what the next graph shows. And you say Peru, you see Peru that was really low here, because that population is smaller. If you divide the number of cases by the smaller population, the rate gets closer to the rates of, for example, Brazil. And the US is still really high, even controlling for the size of population. So here we got the number of new cases in each one of these days, divided by the size of population and multiply by 1 million. Why we multiply by 1 million? Otherwise, these numbers here would be really small. So this here is saying 700 new cases per 1 million population. That's how you read it. And because this data oscillates so much, because there is problem of reporting, this data has been reported as a 7-day rolling average. We get 7 days, get the average, and then take out the previous day, the next day, average among the 7, and then keep moving, and we get these more smooth curves. But even doing this 7-day average, we still have a lot of oscillations. That's really clear in the case of Peru. For smaller populations, we have more issues of reporting, like really small differences from one day to the other causes these oscillations. Okay? Another information that we can get, deaths. And again, just total number of deaths, new deaths for a specific case. The US, back around in April last year, was high, increased again around summer, around Thanksgiving, Christmas, decline a lot the beginning of this year, and now increasing again. And see that this level here is actually higher than the level that we had back in last summer or the beginning of last fall. And last summer, the beginning of the last fall, we were much more strict about social distancing and masks. But looking at the data, what the data is showing that more people are dying now in the US than in the same time last year. And same time last year, we are more strict than now. That's completely counterintuitive if we think about science. And in India, again, a lot of cases, or not a lot of deaths. And the data on cases is really related to the number of deaths, right? But again, it's hard to compare countries with different populations. Let's get death rate. New deaths per day, divide by the size of the population, multiply by 1 million. So this 25 here means 25 people dying in that specific day, in that specific country, per 1 million people in the country. If we look in the US, since we are just looking within the US, we see that the death rate now is higher, August 31st, than it was back in August 31st, around here. This is August 31st last year, around here. This is August 31st now, higher deaths. You could say, oh, no cases, we are all vaccinated. No, deaths, data, reality, facts, right? Another term that you might have heard, that whenever we have this kind of pandemic or epidemic, we should kind of try to flatten the curve. What does it mean, flattening the curve for a specific indicator? In this case, the case of people infected by COVID-19. You pretty much just get the number of people with cases. This specific indicator could be any indicator, and you take the log of that variable. The log of the variable is going to make the really high numbers to kind of lose a little bit of their strength. That's why here, after around February, March 2020, you have a more flattened curve compared to this period here when the pandemic started. Okay, the number of cases are increasing, decreasing over time. We see this, decreasing, increasing, decreasing, and so on. What we have to do overall in terms of log terms is that this curve should kind of we should flat this curve. The number of cases should not increase as much. And preferably, what we want to do is it to decline. And mostly we also want this log to decline for the other variable, deaths. I didn't put this other graph here. I just put the cases. Positivity rate of tests, the share of daily COVID-19 tests that are positive. High around April last year, and then high around Thanksgiving, Christmas, and then high again now. Right? High again, and higher now than the same time last year, around August 31st. Look at this number of cases of tests that were positive. And you could say, oh yeah, more people vaccinated. Yes, that's really good. This graph here is the percentage of fully vaccinated people, at least the 2 doses of these vaccines that we have. Still really low, 50%, a little over 50% in the whole US by the time now. And this varies a lot by state. In Texas, it's lower than 50%. And within Texas, it varies a lot too. And percentage of people that got the first dose, at least you can also get in this database, in this website, it's around 60% in the US. All right, so it's still a lot of people susceptible to die and to transmit it. Hospitalization, COVID-19 patients in hospital, the same website. Increasing just now in this, like starting around beginning of July, increasing until now. Patients in intensive care unit also increasing. That's why we have seen, for example, even here in Brazos County, we are pretty much at maximum capacity of intensive care units of people hospitalized there. It's intensive care, not just hospitalized. and other source of data. See, to do a data analysis, I just don't listen to one source of information. I have to get data from different sources for my information to get more plausible and complete. And I have to get from sources that are reliable. This one here that I'm going to show for the US is from the New York Times. And here I just put one graph above the other. The one on top is the number of new cases from February last year until August now. I also got in the same day, Tuesday, last Tuesday. And below, the number of deaths. Why did I put this vertical dash blue lines there? Just to show that whenever we got here an increase in the number of cases, a couple of weeks later, number of deaths increase. Number of cases increase here. A couple of days later, weeks later, number of deaths. Cases increase. Couple of days later after this, deaths increase. Oh no, but now everybody's vaccinated, no problem. Number of cases start to increase right here. A few days, 4 weeks later, number of deaths start to increase. Number of deaths in the US per day, similar to the previous website, higher than what it was in August 31st last year, where we were much more strict about social distancing, masks, and so on. So that's scary. This data here, from October 21st, 2020, beginning of last fall, we have the average daily cases per 100,000 people in the past week before that date. We see that most of the cases were more in the eastern half of the US. And then November 23rd, 2020, around Thanksgiving last year, it spread all over the US and more the middle of the US with the higher number of cases. And that's already controlling for the size of population in all these different counties, right? Because we are dividing by the population and multiply by 100,000. And then from last Tuesday, August 31st, higher cases in southern US, including like the Southeast, including Texas, Wyoming as well, Oregon as well, right? This is taking into account population size. Yep.
What's up with Nebraska?
Missing data. They don't have data for that, right? For some reason, there is no data. And also here, like few cases or no cases for all these other counties. I didn't read specifically about that, but it might have in the note, in the footnote of New York Times. What was that?
I understood.
Oh, okay. No, I thought you had the answer. That's good. But yeah, lack of data. Okay. Cool. Current hospitalizations, taking into account the population size, high, Southeast US, here among us. Cool. Where we are, I think we are like around here, Brazos County. Yeah, it's this one here, right? Yeah. Vaccinations, percent of residents with at least 12 years of age that are completely vaccinated. Idaho and some other areas, Georgia, we also don't have data for those places. I showed you the graph, right, of vaccinations more recently, fully vaccinated, a little above 50%. Look at how much it varies in the US. Texas overall, lower percentages than in other areas, then even compared to in the southern border, right? Even Florida, that's experienced a lot of like issues there. Overall, the percentage variation there, it's more spread than in Texas. But of course, Texas is much bigger, and the population, they have different thoughts about vaccination. Risk levels. I don't know exactly how this indicator was calculated. I didn't really read the specific methodology there in this website, but it's an indicator based on percentage of people that are unvaccinated, based also on the amount of cases in those areas and the positivity rate in the tests, percentage of people that are tested positive whenever they get the COVID test. And then they created that scale from low to extremely high. And pretty much like we are there, right? In the extremely high risk of contracting COVID-19. Texas, back to the New York Times as a source. Cases and deaths in the bottom. I did the same. These dash lines, I did it in PowerPoint pretty much. I just aligned the two graphs here in the correct date, and I just looked at them in a very simple way. I just did a screenshot from the New York Times, put this in PowerPoint, organize it, poop, it's there. In other words, it's easy for us to analyze this data by ourselves, all public data. Texas, cases increase. A couple of weeks later, poof, deaths. Cases increase. A couple of weeks later, deaths. Increasing here, number of cases, start to increase here. A couple of weeks later, deaths. Texas, August 31st, same level as around August 31st last year. Texas, where we are, same level of deaths as 1 year ago. Much less strict about the pandemic now than before. Is it based on science? No, not at all. This is science, this is fact. Empirical data, right? Hospitalizations, same thing. The New York Times doesn't report intensive care unit for these graphs here, but hospitalizations due to COVID-19 increasing a lot. And tests per day, kind of not increasing so much, and actually declined around March, right? It declined in March, and then it has been a little bit stable and declining, and increased a little bit now, maybe exactly because of universities requiring people to get tested. Cool. Colleges in Texas, at least in one way, Texas A&M beat UT Austin, just to be mean with you guys, right? Since I'm a UT graduate. Number of cases, Texas A&M, 5,576. Baylor, 4,000. University of Texas, 3,900. Right? All there. And if you go to this website, you can click on colleges here for have cases. Of course, the information is limited when you break so much, but there is information about other places that are clusters of the outbreak, nursing homes, prisons, food processing plants, and so on. And here is selected only the top, the colleges in Texas with the highest number of cases. And so that's sorted there by the number of cases. Cool. So this is an example of how you get micro data about a pandemic every day, and you can get that information per state, per county, per college, and analyze that specific issue, right? Break it down by day and so on. And then implement public policies. But when public policies don't follow reality, then everything gets messed up. Whenever we are doing demographic studies, I mentioned to you that here in this class, we are more focusing on social demography. We are trying to link demographic indicators, demographic variables into other variables from other areas, from economics, sociology, geography, and so on, right? When we are just analyzing demographic data and comparing demographic variables to each other, we call those studies formal demography. Whenever we have demographic variables and we try to relate them into variables from other areas, we are doing social demography. And whether the demographic variable is a dependent or an independent variable, that's why in this classification here, we are calling it population studies 1 or 2. So see why those terms variables, independent variables, and dependent variables were important at this point, right? To better explain this. So when both my most important independent variable that I'm trying to use as the explanation of variations in my dependent variable, and that dependent variable is demographic as well, I'm doing an analysis of formal demography. For example, I want to know if specific areas that have higher percentage of young adults, I have higher birth rates than in other areas. Or I want to know if areas that have high birth rates will affect the age composition of that population in the long term, in the sense that having higher birth rates, more babies being born, in the next few years, you're going to have a higher percentage of children in that population. It affects age composition. Look at 1 and 2 here. When I can use both the age composition, this example, as an independent variable in this study, and here as a dependent variable, and the same thing for birth rate, I have a reverse causality in which the first variable explains the second, but this variable also explains the first. I have reverse causality. Economists use the term endogeneity. I have an issue of endogeneity. It's hard for me to know what is causing what. Is it age composition that affect birth rate, or is it birth rate that affect age composition? When I have this issue of not knowing exactly the direction of causality, I'm just doing an analysis of association. Association, I'm saying there is an association between age composition and birth rate. I don't know what's the cause and what's the consequence, but both of them are demographic variables. So I'm doing the study of formal demography. Migration and income. You could say that more immigrants come into a specific country, that could affect the income of specific subgroups of the population because they will compete for same jobs. In that case, migration is affecting income. But countries that have overall higher levels of income attract more immigrants. So income also affects immigration. So in this case, again, I have reverse causality, right? This example, income and migration, is not formal demography, it's social demography as the ones that I'm going to show, but I'm just giving this example to talk about endogeneity, reverse causality. To show that in this case too, I'm not saying that this variable causes that, I'm just saying that this variable is associated with that. One increase, the other one increase, or one increase and the other one decreases, right? There is an association, I just don't know what's the cause and what's the consequence. Another example of formal demography, I could get a sex composition of immigrants to a city And if I have more men coming from other countries or from other states into a specific city, in migrants to a city, that might affect the sex ratio of the total population of that city. Sex ratio is what I mentioned in the last class? The number of men divided by the number of women. When I get the number of boys born in a specific year divided by the number of girls born in a specific year, that's sex ratio at birth. When I get the whole population, men divided by women, sex ratio of the overall population. What this analysis is saying is like, if I have people moving to that city that are more proportional, a lot of men, that will affect the overall sex ratio in that receiving city. Both of these indicators, both of these variables are demographic, so that's an example of a formal demographic study. Example of social demographic studies. Well, here we are calling it Population Studies 1. Is when I have a non-demographic independent variable, my most important independent variable, explaining a dependent variable. I want to know, for example, if people with higher, like upper social class, have lower death rates. Death rates related to mortality. It's demography. Social class is a sociological concept. And I remember first, like when I was taking introduction to sociology and I was an undergrad student, the professor said, what is social class? Oh, there's a social class walking right in the hallway right now. Can you see it? We cannot see it. We have to come up with a concept of how we measure social class. It's a construct, a concept, based maybe on income, based maybe on place of residence, on occupation, and so on. Right? But it is an indicator, sociological indicator, trying to explain the effect on non-demographic indicator. Attitude about motherhood, a social psychological variable. The attitude about motherhood from women might affect the number of children that they want to have and that they will have throughout their reproductive ages. The rainfall, because of climate change nowadays, there are a lot of studies showing if increases in annual rainfall, if that makes people migrate out of specific areas, affecting population density. In this case, making population density decline. Population density size divided by the size of the area. So a geographical variable explaining a demographic variable. Economic opportunity, in whatever way that you think about what is economic opportunity, how do you estimate that indicator? Could be employment rate. It could be some other kind of like economic variable that gives me an idea of how are opportunities for people to get jobs in a specific area. When economic variable, economic opportunity will attract more migrants to a specific area. So economic variable influencing a demographic variable. And the opposite. When I have a demographic variable as being the independent variable and a non-demographic variable being the dependent variable. Age composition, usually areas that have higher proportion of younger people, that changes voting behavior because younger people in general tend to be more progressive. Migration, areas with more migrants bring new ideas to specific areas, and that might generate social change, demography affecting sociology. Birth rate, increasing birth rate, demographic variable might make us need to invest more in hospitals, in public health services for children, for babies. So, demographic variable affecting our actions in public health. So just to show that demography We can analyze demography within itself, but you can think about all sorts of examples. The microphone goes crazy if I move too much. We can think about all sorts of examples of demography with each one of your majors, right? That's what we are showing here with social demography. Next topic, something that demographers always use these terms, cohorts and generations. Cohort is a group of people who have experienced a common event during a given time interval. So people who are born around the same time, they are a cohort based on birth, time of birth. And these people, cohorts based on time of birth, are called generations. Now here at the MSc, if we go there are some t-shirts to sell. Let's say class of 2025. The class of 2025 is the cohort of people that entered A&M in the fall of 2021. And that's actually a policy of the university to make people finish fast in 4 years, to don't delay, right? Graduation. But that's an example of cohort. Not birth cohort, but the cohort based on the semester, on the academic year that people entered A&M. Why do we care about cohorts? Or more specifically, why do we care about birth cohorts? Why do we study people born around the same time together as a group? If you understand what distinctive opportunities and problems you have faced, you can find common ground with others in your own generation and in other generations. Of course, we all here experience, even you all being born around the same time, you all experience life and issues and challenges in different ways. But overall, you are exposed to the same problems, to the same challenges, to the same society, to the same pandemic, to the same university, to the same state, to the same governor, to the same president, right? To the same opportunities. As a whole, of course, those opportunities vary a lot individually, and they vary by population. But overall, we can have an idea of how this birth cohort is experiencing problems and challenges throughout their time. So there are different classifications of cohorts. This is an example here for the US. So some examples, and these classifications here in terms of time, it varies a lot. So it's not a really set time here. I'm not actually asking you to memorize these years. It's just to have an idea. People born during the same period who experience similar social circumstances throughout their lives, they usually are classified within the same birth cohort. The good warriors or the greatest generation, you're born in the 1900s through the 1920s. So they faced the Great Depression in the 1930s. They fought in World War II when they were already young adults. The lucky few, those born around 1929 and 1945, exactly when they were born, it was the Great Depression, World War II going on, fertility declined a lot. These people overall were smaller number of people than previous generations. By being fewer people in their society, they compete less for jobs and for economic opportunities. So they're the lucky few. That's why that's the reason of this name. Baby boomers is the opposite. After World War II, where everybody, economy growing, new hope for a new society, let's start again. Between 1946 and 1964, fertility increases a lot. A lot of people being born. And these people, when they enter the labor market at the beginning of the 70s or end of the 60s, they have more people, they're competing for jobs with more people And baby boomers also have better educational attainment than previous cohorts. So more well-qualified people and more people in general. So they face issues. And those people are still here because they are retiring now. And then a higher percentage group of population facing the retirement issues as well. Generation X, or baby bust cohort, fertility declines again. I'm from 1977, so I would be classified here. Millennials, or new boomers, or Generation Y, from early 1980s and early 2000s. Generation Z, starting in the early 2000s. I think you're all guys are Generation Z. Oh, that's crazy. I'm really old. Just the date of birth of my students. And so just an overall idea of how we can classify birth cohorts. The lucky cohort, they were fewer compared to the much larger numbers of people in the following cohort than compared, for example, to the baby boomer. The baby boomer, when we have increase in fertility, and that cohort increased a lot. The smaller size of the lucky few has enabled them to experience higher employment rates, greater variety of social opportunities than members in the preceding and following cohorts. Okay? This table here, I got it from a short article that Dudley Poston wrote recently. 2020, September last year. Kind of also trying to summarize these different cohorts from New Worlders until Generation Z, years of birth, age range in 2020, number born in the US, the total, alive in 2019, including immigrants. That's why this number here is higher for millennials than this one here, because a lot of people immigrating to the US that were born in other countries between these years. And then the number of people born in the US, these guys here, per year. So we see baby boomers increase a lot from 2.5 in the lucky few per year to 4 million. And then it declined again, Generation X and millennials and Generation Z increases a little bit, but because the overall size of the population is big. So that's why the number of people being born is not necessarily because there is an increasing trend in fertility. It's just because we have more people nowadays comparing to 46 and 64. But you see the decline per year from the baby boomers to the Generation X, 4 to 3.4, and the increase from the lucky few, 2.5 to 4 million born in the US per year. This is a graph that also summarizes the same trends, just showing the 7 US cohorts by size from the year that they were born, in 1900s until 2010. New Worlders born like farther away in time, and then the new boomers more recently. And this is the overall size of the population. And you see here the jump from the lucky few, the green, into the baby boomers, the light blue. So that jump, because of end of World War II, you have more opportunities for people, infertility increases, more opportunity and all that. And that will affect the population for the next decades, okay? Another way to show that, there was a trend and increase in the overall number of people born per year because the population increases overall. Mortality declines, people live longer, and even with like similar levels of fertility, you have an overall increase in population. But then you have this jump from the lucky few to the baby boomers, all right? The same way to show that previous graph in another way. And this next part is going to be more technical, and that's outside of the textbook. So I suggest you taking a look at these slides before the class. And of course, all these chapters that we are looking at, I suggest you reading the chapter before coming to class so you better understand it. But the Alexis diagram is pretty much a graph that we try to understand different ways the population in the specific year, or population over time, or a specific age group over time as well. Okay, so it's 2 p.m. Thank you very much. Have a great weekend, and I see you guys on Tuesday.